Our first guest this afternoon needs little introduction, but I will. It's Mr. Mike McWillians, Senior Project Manager from ARRIS with OBI in the RF network. Mike McWillians is a Senior Project Manager, end-to-end RFoG HPOM portfolio with ARRIS, formerly Aurora Networks, using significant technical background and experience to optimize solutions for the cable operators globally. Prior, he was a sales engineer based in Europe, providing technical support and design services. He started his career in the cable industry in 1993 with United Artists Communication, moving to NTL, now Virgin Media, where most notably he was head of access network engineering, specializing on all aspects of the access technical transmission layer, which included telephony, Ethernet, and the HFC plant. Michael is widely acknowledged as an industry expert, having been listed in Cable and Satellites Euro 50, along with representing the UK in European Senelec technical committees. Thank you, Michael. Over to you.
Thank you. Thank you, Paul. Good afternoon. Hope you all had a good lunch. I'm here to talk about OBI and RFoG Networks. Where's the little machine? So I'd like to go through OBI. What is it? What it causes, some analysis of its causes, how do you identify it, what can you do to stop it, mitigation, and what's the solution to OBI in an RFoG network? First question, and it's a question I've been asked an awful lot, is OBI a problem in an RFoG network? Well, I suppose the answer is it depends entirely who you ask. If you ask an operator who's just built an RFoG network with very few customers, OBI isn't a problem. If you ask an operator who's got a network that's approaching 80% capacity on RFoG, OBI then becomes a problem. So OBI is a problem. It's always there in an RFoG network. The question is, what can you do about it? So let's look at what is it, OBI, the causes. Basically, OBI occurs when two optical transmitters of the same or very similar wavelengths are seen at the same receiver. Just to go into a bit of maths, and there won't be that much maths because this is condensed from about 5 papers to get to some of these numbers. But if you look at the output from an an optical receiver, the current from the optical receiver is represented by that, which is the energy of the two signals and the receiver responsivity. To move it a bit further along, if you express it as a power, you have your two wanted signals, and this is the OBI element. And this is always there in an optical receiver with two optical signals coming into it. The key thing to look out for here is there are two elements that cause OBI. There's the polarization difference between the two signals, and there's the wavelength difference between the two signals. Largely, we tend to ignore the polarization because we can't really control it, but you can control the wavelengths. And the wavelengths difference becomes critical. So we look at the slide we have up there, the two wavelengths. So if we take two 1610 return transmitters, one at 1610 and one at 1610.25, you actually get the frequencies of the two. And you see from up there, there's a 30 gigahertz separation between those two signals. Well, that 30 gigahertz separation is not going to cause any problems because it's outside the receiver bandwidth. But there's a couple of other things to consider in a return transmitter. In fact, in any optical transmitter, transmitters have what they call chirp on them. This is a signal introduced into a transmitter to improve the second-order distortions. And it's this chirp which produces a Gaussian noise signal when the two are combined. The other thing to look at is how far apart are they and what is that chirp frequency. Now we've investigated and measured the impact of BER of the chirp signal and how far between the frequency offset measured as a measure of the chirp. So if we take two optical signals, lambda 1, lambda 2, each of them carrying two RF signals that you're interested in, if you say they're 1 gigahertz apart, the output of the receiver produces this effect. So you have the two wanted signals, here and here, and you have this Gaussian noise that's generated due to the difference of those two frequencies. If the distance between the center of the noise is less than 4 times the chirp away from the signals, this noise figure starts becoming prevalent, and you see it in the return signal. And that is the OBI noise generation here. This is what generates the OBI. So if you've got 30 gigahertz spacing, as we showed at the top, this is centered at 30 gigahertz. Although it's in the receiver electronics just ignores it because it can't handle a 30 gigahertz signal. So it's only when the separation of these two signals gets closer together that this noise starts being introduced into the return path receiver output. So to put it simply, if the interfering signal is more than 4 times the chirp frequency, there's no impact. But as it gets less than 4 times the chirp frequency, the BER starts suffering significant impacts. And the chirp frequency on a return transmitter is around about 250 megahertz. That's dependent on the transmitting. The chirp frequency is dependent on the transmitter power. So for higher power transmitters, that chirp frequency is increased. And that's pretty much it for the maths. But what does it look like in a network? If I take my 2 optical signals, here and here, separated with a nice healthy separation, I get my signals and I get a really good noise floor and no interference. But as the 2 signals start to overlap and get closer together, you can see the noise floor comes from here, comes up to here. And worst case, this is about 5 or 6 dBs below the carrier level. So it's so bad, it actually kills all the signal. There's no error correction that can work with a system that's only got a 5 dB CNR figure on it. It just doesn't work. So every time it happens, it kills your return frequency. So what causes it? Well, it's 2 transmitters at the same wavelength into the same receiver. In an RFoG network, it's a statistical probability, and there are multiple variables that you need to consider before it happens. So the number of receivers you have combined together, the more receivers you have into your CMTS, the lower the chances of OBI. The number of active upstreams, the more upstreams you have, the greater the probability of OBI. The number of customers, the more customers you have, the greater the chance of OBI. The higher the data usage, the greater the chance of OBI. The other thing to bear in mind is temperature variation. Becomes critical. Return transmitters in an RFoG system, it's a low-cost transmitter. It's not thermally stable. So those transmitters, the wavelength of the transmitter changes with temperature. So we have, 0.1 nanometer per degree centigrade, or a 1 nanometer change for a 10-degree temperature change. The other thing to remember is return transmitter wavelength. Not all transmitters are the same. They're very close. A 1610 transmitter made in the same batch, typically 95% of them will be within 0.9 nanometers of each other. They're not identical, but they're very, very close. And as manufacturing techniques improve, they get closer together. So if you have a batch of RFoG return transmitters, you can assume that they will come from the same batch because you tend to buy them in groups of thousands, so that you'll find these transmitters have a very, very similar upstream wavelength. On the temperature front, you can't assume that all your RFoG transmitters will be at the same temperature. If you put them outside somebody's house, they're either going to be in sunlight, they can be in shadow, they can be inside somebody's house, so there will be temperature variations and they will change during the day. So the upstream transmitter wavelength of your return transmitters, it will vary during the day and it will vary across your network. Now we tried to do some analysis of OBI, the number of receivers, the number of return transmitters against temperature. To make the maths manageable, we made various assumptions in the network. So we assumed the optical transmitters, they're going to follow a Gaussian distribution of each other. We assumed, for the sake of this argument, that for no OBI, the separation would be greater than 4 gigahertz between each transmitter. It's probably wider than it actually is, but That's the assumption we made. We assumed that the number of transmitters was always on, so there's a single MAC layer with DOCSIS 3 with n number of bonded upstreams, so 1, 2, 3, 4, 5 upstreams on at the same time. And we also assumed that the traffic was at maximum, so that the system links were running at 100% capacity. Now, no network runs at 100% capacity, or at least it shouldn't. So what did it all end up with? Well, as you can see, if you have one, whoops, what's just happened here? Oh, there we go, wrong button. If you have one transmitter on at the same time, you can never get OBI. So your probability of OBI is 0. But as soon as you start increasing the number of transmitters, OBI starts to increase. And there is the temperature element. If you can assume that all your transmitters stay at exactly the same temperature and they never vary, chances of OBI happening are really quite low because they're fixed and locked, as long as they're not identical. But as the temperature variation between them increases, those wavelengths move. As they move, they overlap other transmitters, so the incidence of OBI start to increase, which is represented by the blue line here. And this is a 10-degree temperature variation. This is an extreme one, but in a typical network with 4 upstreams, probability of OBI can be getting up to 25%. Now that's probably too high for an operational network. The other thing to remember, because the noise from OBI is so extreme, when OBI is present, the data throughput to that CMTS port, that anything connected to the same CMTS port, the data throughput is 0, because it's an RF-generated signal. As you combine the RFs together, this noise is seen at the input to the CMTS port, so any RFoG device connected to that port, the data throughput will become 0 during the instance of OBI. So, worst case scenarios. For lower traffic loads, the percentage probability of OBI, you can reduce it with your data throughput. So if the data throughput is running at only 50%, your chances of OBI drop by 50%. And that follows all the way through. So 10% usage, your 25% chance of OBI is down to 2.5%. So it's very much dependent on the data throughput that you're using. The other point, it is dynamically changing in your network because of the temperature changes of your RFoG ONUs. So you never quite know where it's going to happen, and it's very difficult to find it or identify it. But identifying it, you think you have OBI, how do you find it? Well, it's a short-term burst phenomenon. Because RFoG ONUs, they are burst mode, OBI only occurs when 2 of them are transmitting, and the transmission durations for DOCSIS 3 typically very short, so it only occurs for very, very brief durations, and it increases with usage. So the easiest way to find it is actually to look at the CMTS. If you look at your CMTS data, that will report the number of uncorrected packet, it will report the number of code word errors or uncorrected code word errors you're seeing in your system. Now, in a normal operating system, the number of code word errors should be significantly less than 1%. Typically, it should be around about 0.1% in a normal network. It should be very, very low error count. So that's one way of finding it. Second way, and probably the easiest way, is to use a spectrum analyzer. It's very, very obvious, and it's very, very easy to see OBI on a spectrum analyzer because it's a very, very characteristic noise pattern. To show you what I mean, this is a real network. This is a trace sent to us by a network in the US, and they were complaining about OBI. So they have their 2 upstream carriers, as you can see. Well, I've done it again, wrong button. They're 2 upstream carriers, one here and one here. The white trace is peak hold on the analyzer. The orange trace is the noise. Now, it's a very, very noisy network in this particular network, but they were complaining about OBI. So they put the spectrum analyzer on, they put it on peak hold, and this is what you see. You see the noise spikes across your whole RF spectrum, but on the peak hold trace, you can see the noise floor 5 or 6 dBs down from your carrier. And it's a very characteristic trace. If you have OBI, it'll always look like that if you use it on peak hold. It's another one. Another active network, again in the US, 4 upstream carriers on here. You can see the OBI here and here and here. It's the characteristic noise spikes that occur across your whole RF spectrum. And it's only there when they're transmitting. When it's there, it's corrupting the data on all 4 of these channels. Challenge you have is of those 4 channels, which 2 are causing the OBI? And actually from this, you just can't tell. You just can't identify which 2 transmitters are causing the problem. Could even be 3 transmitters causing it, but you just don't know because you know it's going to move. So it's almost impossible to identify the return transmitters that are causing the problem, which makes it an interesting challenge in a network because as you add data capacity to your network and you add customers to your network, this starts to increase, and it impacts your data throughput quite significantly. So, in an RFoG system with a single RF upstream carrier, so it's not using 4 bonded carriers, you can never get OBI. The CMTS will control the upstream transmitters to only allow 1 device to operate at the same time, so OBI can never be an issue with a single upstream carrier. But when you have more than 1, you're going to get some OBI-generated packet loss. The question is, how much can you live with? Well, if it's just data, for a lost packet, the system will start retransmitting. So from a customer point of view, it's probably not going to be too serious for low error counts because the data will be retransmitted, so when they hit the send button on the email, if it has to be retransmitted, the customer doesn't know. Oops. On voice calls, I still haven't got some definitive answers on this, but if it's large enough, it will be sufficiently large enough to call the voice call to drop out. Somebody wake John up, will you? So for an active voice call, if OBI is sufficiently high enough, it may cause the voice call to drop out. It's unlikely. You might lose a little bit of data throughput because in a voice call, they don't resend packets. If you're sending video streaming, you're going to see holes in the video. You're going to get errors. If you're running a VPN network, figures I got back from one operator, if the packet loss is above 5%, they're seeing VPN connections start dropping out of their network. So that starts to cause a major problem on those networks. So what can you do about it? What can you do with a standard network to mitigate and try and get rid of some of these problems? So what variables do you have in your network that you can control? Well, you can control the number of upstream carriers that you have active on your network. If you can increase the bandwidth of each of your carriers, so going from 64 QAM, go to say 128 QAM, 6.4 megahertz bandwidth, with less upstream carriers, you'll reduce the incidences of OBI. Still be there, but you may be able to live with the numbers. The other thing you can do, maximize the number of optical receivers that you have. So instead of having 1 or 2 receivers, increase the number of optical receivers into the CMTS port, but maintain the same number of connected customers. It's the same thing, you reduce the number of customers per receiver. If you've got 32 customers into 1 receiver, the chances of OBI increase. If you drop that from 32 to 16 and double the number of receivers, your incidence of OBI will reduce by 50%. So that's one other method you can do. However, all of those options impose limits on your upstream bandwidth, and they limit the service to customers. And quite frankly, that's not a particularly good business model to have. It's actually you're building a system with a restricted upstream bandwidth, which as you increase customers, is only going to get worse. DOCSIS 3.1, we've all heard about it. It's being implemented. Network operators are beginning to implement DOCSIS 3.1 into their networks. How's that going to impact an RFoG system? Well, you know, DOCSIS 3.1 uses OFDM upstream modulation, multiple small carriers at 25 or 50 kilohertz carriers. Individual cable modems are now allowed to use small chunks of that carrier. In fact, I believe DOCSIS 3.1 will allow up to 40 simultaneous users at any one time if you're deploying DOCSIS 3.1. So that you have individual bandwidths. I think it's 200 kilohertz is the smallest bandwidth per device, up to maybe 90 megahertz if you're using a full system. So with 40 cable modems, your incidence of OBI increases with the number of upstream channels. I showed you the graphs earlier for the incidence of OBI and the probability of OBI with 1, 2, 3, and 4 channels. I got the guy that did that curve to extend it, to bring it up to the 8, 16, or 32 channels. And as you can see, when you get to 32, it's not actually 100%, it's 99.9 something or other, but as near as, damn it, you're going to have OBI. Almost certainly. You're not going to be able to avoid it. So, to support DOCSIS 3.1, you do require a full OBI-free solution. You can't run DOCSIS 3.1 in a system which has got OBI in it. Not if you want to run 40 cable modems and make the maximum use of the available upstream capacity in DOCSIS 3.1. I mentioned it has an impact on data services. Looking around, and I asked some of the experts back at the office, and somebody came up with this particular slide for me. The SLAC, which is the National Accelerator Laboratory, Stanford University, they did a survey in 2007 looking at the impact of packet loss and data throughput. I believe it was one of the largest surveys done on the impact of this, and it was a huge survey, and they spent 6 months collecting the data. And this is what they produced. So this is the results of that survey. As you can see, as the packet loss increases, the data throughput drops. But it's not really terribly easy to see what that actually means in a real term, because it's a logarithmic scale. So I got them to redo the plot. And that's what it does to your data throughput, for TCP data throughput. For the impact of resend traffic on a data throughput for a channel is very, very significant. You'll see there are 2 curves here. The 2 curves relate to which of those 2 represents that slope. The purple one is this one, and the black one, I think it's that one. So the 2 best fit lines for the data throughput. So, where's it gone? So let's just put 2% packet loss. So if we have a 2% packet loss on your data throughput, that's the impact. Somewhere between 48 and 68% packet loss at 2%. 46 to 68% loss of data throughput with a 2% packet loss. Even at 1%. 15 to 55% data throughput. So what's the input of OPI and that packet loss? It's actually very, very significant on your data throughput. Most of the operators I'm aware of, so around about here, they start looking at segmenting a network. If their data throughput is approaching 80% of capacity, it's time to segment the network. With 1 or 2% packet loss, you're not even there. Your system's broken before it's even started. So yes, you need to do something about OBI if you want to improve the throughput on your networks. So for true OBI operation, you must manage your system to eliminate the chance of the 2 optical transmitters operating at the same wavelengths being seen at the same receiver, at a common receiver. To date, I'm only aware of 2 principal technologies of getting rid of this. First off, you can use the active optical splitter. So it's multiple receivers, sometimes known as an MDR, multiple diode receivers, in which case you have 1 receiver per transmitter, and with 1 receiver per transmitter, you can never get OBI because it's only connected to 1 receiver. It's the same as the rest of your network. OBI is 100% eliminated. The second option is to control your upstream wavelengths, so that the 2 upstream wavelengths, so they never occupy the same wavelength, and you separate it out that way. If you're using multi-diode receivers, your first option, So it's an active optical splitter. Typically, they have 32 receivers in them, one receiver per RFoG ONU. And in that situation, OBI can never occur. Comes with a few penalties. It requires a powered cabinet. It's an active device now. You no longer have a passive optical network. Typically uses standard 1610 RFoG ONUs, which is actually a good thing because it's a much lower cost device. However, it doesn't support a distributed optical passive network. Why is that important? Actually, it's in your build costs. If you have one of these devices in your network, you have to bring all your customers back to a standard cabinet. Typical designs we're seeing, they're bringing 256 customers back to an active cabinet. Each customer, to get to that customer, typically there's four optical splices per customer to bring it back to a common cabinet. I don't know what the costs are for an optical splice, but in the US I've heard figures of $27 a splice. What that means, there's over $100 of optical splicing costs just to get these customers back to a common cabinet. And it actually adds significant costs to your RFoG build. So it increases the cost of an RFoG build. One advantage it does have, though, it supports PON overlay. Because you're operating in the 1610 domain in the return, you can support the full 10G or 1G PON networks so that you're building an optical network that it becomes future-proof so you can start deploying a PON network at a later date. The other option is to control your upstream wavelengths so that your individual upstream transmitters no longer operated exactly at 1610. Each of them is operating at a unique wavelength. Because they're in unique wavelength with sufficient separation, OBI is also eliminated. There are some limitations. There's a limited wavelength selection available. There isn't a 32 wavelength solution commercially available just yet. The other issue, you have to manage the wavelengths and allocate the wavelengths. So if you're building a network to an SDU customer base, you have to know which wavelengths you have deployed already so that you don't deploy the same wavelength to the adjacent customer back into the same receiver. That just becomes an operational practice that has to be implemented in the network if you go this particular route. And it has to be done at installation. Because we've only got a limited number of upstream wavelengths, it requires an additional return receivers. That in itself isn't typically too much of an issue. But one advantage, you can now mix it with the MDR, the multi-diode receivers, and you can combine a multi-diode receiver option and a multi-wavelength solution at the same time. So instead of having 32 MDRs, a 32 diode receiver looking at one customer, you can have that one diode now looking at 4 or 8 individual customers, each of them with a separate wavelength. So it allows you to eliminate OBI in that aspect as well. One advantage, it allows you to start using a distributed optical network. So instead of bringing all your customers back to a central cabinet, you can bring them back to a smaller passive cabinet, combine the multiple wavelengths into a single fiber, and bring that back to your central point, which gives you significant savings in your build costs. There are two ways of doing it. You can do it in the 1610 window, and in the 1610 window you actually manage the upstream wavelengths of the 1610 transmitter. You thermally stabilize the transmitter, lock it to a fixed wavelength, set it to a wavelength, typically 1 to 16. The advantage of that one, because it's operating in the 1610 nanometer window, you leave the rest of the wavelengths free so you can deploy a PON network onto it as well at a later date so that you can allow migration to a PON network further on in time. The other option is to use a CWDM waveband. If you're using the CWDM waveband, you're making use of the multiple CWDM wavelengths available. Disadvantage, you have to have multiple RFoG ONUs. You have to have one for each CWDM wavelength. The other, probably more significant concern is if you're starting to use multiple CWDM upstream transmitters, you do severely limit how you can deploy PON at a future date. So this particular option, unless you design it very, very carefully, you can end up with a network that will need a rework to allow PON to be deployed in the future. There we go. Questions?
Thank you, Michael. That's quite an interesting presentation on OBI there.
I hope it helps.
Do we have any questions?
Please.
At least one.
At least one, yes.
I'll shout as I can. Way back in the old days when optics was first invented, I think people did try to use a single receiver for multiple optical returns, and without any precision or anything, and it was a big no-no because it just didn't work. Because obviously, if you got two returning wavelengths, they were not precision, but if there were things sort of optical beat of the RF coming out of the receiver, you would get rubbish. And as these things were sort of they were FME and everything, fabric aero laser,
If it's
cheap and cheerful, and it just didn't work.
FM introduces its own significant problems. FM return transmitters.
No, not FM. This was incidental FM.
Oh.
The things, the self-FM bar not meant to be amplitude modulated, but of course the things used to wobble anyway. The laser was mounted on jelly, and the thing.
I don't think my memory goes that far back, but I can, yes, if the upstream transmitters isn't stabilized, and if it is just moving around, they move around with temperature. The temperature changes with use, so as you turn a transmitter on, the temperature of the actual transmitter starts to move, so there's a spike in the usage, so the temperature shoots up, and then the cooling system comes into play and brings it back down again. So if it's on all the time, they tend to be static, but in the burst mode, you can get this sudden burst. As they come on, you will see frequency variations of the wavelength.
But most cheap and cheerful return transmitters, basically they're sort of directly modulated, and they're meant to be FM, and they just splodge everywhere. It's only when you get some precision externally modulated that you get the sort of clean spectrum from out.
Well, certainly in the old Fabric Pro, if you looked at a spectrum, the output spectrum of Fabric Pro transmitter, it's got horrible amounts of sidebands that are coming out the side of it, and those sidebands can also cause a degree of OBI. And again, they will vary with temperature, so you've actually got sort of two wavelengths sort of doing this all the time, so you will get all sorts of horrible effects coming out of it.
This is going back to the late 80s, the early days of optics.
I think they're a bit better now.
Oh, right, okay.
Any more?
Please, Mike.
Mike, it's a slightly analogous question, really. The graph you showed showing the decrease in throughput versus the number of receivers that adds up.
Yep.
This is an illustration of the optical domain. Keep going backwards.
One.
That's the one there,
Yep.
yeah. Do you think there will be an analogous effect in the RF domain with two RF carriers operating on the same frequency, as far as that graph is concerned?
Well, this is just data. This is just the impact of it. This is the TCP data. So if any system that's using a TCP data with a resend, it's the impact of the multiple resends that's killing your data throughput.
Yeah.
If you're not using TCP, then they don't send resends. So voice calls, VoIP calls don't use TCP. So they won't cause this effect, but they could well be caught out if your data throughput starts to increase. The fact that you're losing this much throughput through TCP will start to impact on your voice calls, will start impacting on voice calls as well. So it's actually, this is a data effect, and it's nothing to do with the transmission medium. It's purely the effect of data throughput and packet loss.
Thank you.
Mike, an observation rather than a question. Yeah, we've done fairly significant testing on this, having recently deployed a number of RFoG networks and kind of going to town on deploying some more.
Yep.
And I would love to see the detail that gets you to the 2% packet loss, giving you that level of loss of throughput.
That's these guys. This is where it comes from. This is the Stanford University research they did, and they measured the impact of packet loss and throughput.
Yeah, is there a white paper that you've taken that from that you point me in the direction of? I guess what I'm asking.
If you look up these guys, this is a published white paper from them on that research. So that's why I've acknowledged it at the front, because I actually listed it from that research paper. Somebody pointed it out to me last week, so I brought it in. So this is the research that somebody else has done in 2007.
Right. Okay.
I mean, it's a scary graph. I mean, quite frankly, if you look at it's the impact. But we've always known that data loss has a significant impact on throughput. We've seen it in the networks for years. And it doesn't take very much to start killing your network throughput. Once the retransmits start to happen, you're continually swamped by retransmit signals over and above the normal data. So your network's still transporting the same amount of data, but now 80% of it is resends from the transmissions you're already trying to send. That's what you're seeing.
Is the congestion avoidance algorithm kicking in to reduce the throughput of TCP, so a small amount of packet loss reduces the speed by a massive amount?
It just is. I mean, this is the research that these guys did. This is nothing to do with ARRIS. This is just a research project that the Stanford University did, and it is available. If you look it up, you can find that paper.
Okay, thank you. Thank you, Mike.
Okay, thank you.